Okay, so we will now jump on to processor design. So far we have looked into assembly language and we have gone into details of understanding the simple RISC assembly language. Now what we will do, we will see how this assembly language actually can be translated into a processor. So we will look into a processor design, and the objective will be to look it thoroughly, so that whatever we have seen the simple RISC ISA, that can be implemented on an hardware. And not only implemented, we will also try to look into the different aspects of how to make that implementation more efficient, power efficient, and so on. So whenever it is feasible. All right. So if you recall, the instructions are provided to the processor as a bundle of 32 bits. Now what we need to do, that binary 32 bits we have to take and we have to execute, or we have to physically implement how that instruction has to be executed. Okay. So the basic approach we will take is basically the instruction, or any instruction will be divided into different stages, and each of the stage will be designed separately and implemented separately. All right. So this is very much like what we have discussed in our initial classes about let us say breaking the task into multiple subtasks, and we spend a significant amount of time in looking into an analogy, like in a student mess, when you go, instead of putting every content in one container, you have multiple containers, and you go from one counter to another counter, and you get your food. Another similar analogy can be the car manufacturing. So automobile industry, the assembly line was actually first very widely used in automobile industry. So there are as the name suggests, it's called assembly line. So the car starts manufacturing at one end of the assembly line. As it gets manufactured, it moves through the assembly line, and at different stages different parts of the car gets assembled, added to, and finally you get a product as car. So similarly we can think of our instructions are basically the basic instruction will have different stages, and those different stages will be executed separately, and for each of these execution we will have separate modules which will do the execution. All right. So let us dive into it. So we will be looking into a processor design, and so as we said, like the basic assumption or basic approach we will be taking, that we will be dividing the whole processor design into, or processing into, different stages. So divide the processing into stages, and we will also design each of these stages separately. So what are the different stages? So we will start with a very simple division. So the processor is divided into stages which are broadly, let us say, the first task you will be doing is instruction fetch. So basically you will have the instruction in memory, so you have to fetch it. So we will call this stage as IF, instruction fetch. After you are done with fetching the instruction, the next thing is basically you have to fetch the operands. So we can call it operand fetch. Sometimes it is also named as decode stage. So basically you understand what this instruction is supposed to do, and accordingly you look at where the operands are and you fetch them. So for simplicity we will call it here as operand fetch. All right. in short OF. So once you have the instruction fetched, operands fetched, the next thing you can do is basically execute. So execute is basically if you need to do, let's say, some arithmetic operation, you do it on the ALU, or you need to figure out some branch outcome or branch address, etc. All these things you can do it here. After you are done with the execution, the next thing is you need to store the data. Basically, or you need to access memory. So let's now just put it down. We will go into the details of what we will be doing in these stages. So memory access will be one stage where maybe where you will be executing the load store kind of accesses. All right. So we will call it MA, memory access stage. And then finally the register write, or register, sometimes it is called write back stage also. Okay. So while we talk about pipelining, which will be the next topic we will be discussing, we will see maybe those exact names will be little different, but broadly this is how we will be dividing the whole processing or into 5 stages. So what are the 5 stages? We will first do the instruction fetch, followed by operand fetch, followed by execution. Then we will have a stage for memory access, for load and store kind of instructions, and then there is a register write. All right. Okay. Okay, so to start with, what do we do in instruction fetch? In instruction fetch stage, we do primarily 2 things. We fetch the instruction from the instruction memory, and we also compute the address of the next instruction. So in instruction fetch stage, we do these 2 things, basically fetch and instruction from instruction memory, and the next thing is basically compute the address for the next instruction. All right. So pretty intuitive. We will look into how it is done, the actual implementation of instruction fetch in a moment. First we will have an overview of what is done in each of these stages, and then we will look into the actual implementation of each of these stages. All right. Now let us look into the OF stage, or operand fetch stage. So what do we do in this operand fetch stage? So the first thing we do is basically we first decode the instruction, because we already know that the instruction is 32-bit, the upper 5 bits. So basically the bit number 32 to 27 are reserved for opcode. So by reading those 5 bits, we know that what this instruction is about. If you remember, like in simple RISC we have 21 instructions, and to encode this 21 instruction we need at least 5 bits, and that is where those 5 bits come from. So first thing in the OF stage, what you need to do is basically decode the instruction. Decode the instruction. So it also means that you basically break the instruction into different fields. So we already know, depending on the instruction, that there are specified fields, and for example, where my source registers will be, where my destination register, what is my destination register field, and so on. The next thing you will do is basically you will fetch the register operands from the register file. So you will know that, okay, in the instruction maybe you are trying to add two registers R1 and R2. So, you have to fetch those source registers from your register file. So, that is the next thing you will be doing. So, you fetch the register operands from the register file. So, in simple RISC, the register file contains 16 registers. Now, in this OF stage, you also need to do few more things. You might need to compute the branch target if there is a branch instruction. For example, let us say there is a unconditional jump instruction. So, in that case you will be given branch to a particular offset value. Then what you have to do, you have to add that offset value with the PC to figure out what will be the new PC. So, basically you need to compute the branch target and how do you compute it? Basically PC plus offset is your branch target address, and that is what you need to do. Now, apart from that, how about if the operand is an immediate value? So, we know that immediate in simple RISC the immediate was 16 bit, and there were two modifiers, basically 2 bit modifiers. So, that conversion, so basically converting that 16 bit immediate value to a 32 bit value is also done in this OF stage. So, you compute the immediate So, what is the immediate? 16 bit plus 2 bit modifiers. Now, just to remind you, there were by default, if I need to convert this 16 bit to 32 bit, the default modifier says that you extend the sign bit, right. If there is a U modifier, that means it is unsigned. So, you just add zeros in the upper 16 bit. If it is a H modifier, then this 16 bit will be placed on the higher 2 bytes, and the lower 2 bytes will be replaced with 0. All right. So, I hope all of you remember. So, basically the conversion of this 16 bit to 32 bit is done in this OF stage. Okay. And of course, you need to generate different control signals, which we will be discussing later. So, if you intuitively look at it, you see that this decode stage or operand fetch stage is pretty extensive. So, what you are trying to do in this stage, you are looking at what is the instruction, depending on that you figuring out what are the operands required. Sometimes it may be a new branch target that you need to calculate, because if it is a unconditional branch or call instruction, or let us say a return instruction, in all those cases you have to update your PC to a new location, and that PC needs to be updated with some offset. So, that you might have to compute. If there is an immediate operand, then this immediate operand needs to be converted to 32 bit, looking at all the modifiers and all these things, and you have to generate few control signals, which we will be talking about in a bit. All right. So, this decode phase or the operand fetch stage is one of the most time consuming phases. So, if you consider this as your different pipeline stages, you see that in instruction fetch stage you are just fetching instruction and you are computing the next address, which does not require that much of time. if we look at the hardware, it will become even more apparent, but in the operand fetch stage you are doing lot more, and that is why intuitively we can make a comment that it might take more or longer time to execute this stage. Alright, so we will come to that in a bit. Now the next stage is basically execution stage, which is as we can intuitively understand that it will contain the ALU. So we are talking about the execution stage. So it contains the ALU, arithmetic and logic unit. Now this unit performs all the arithmetic operations like add, add, subtract, division, comparison, mod operation, all these things. So it performs all arithmetic operations like add, subtract, multiplication, division, compare, then mod, all these operations. It also performs all the logical operations like AND, OR, NOT, and so on. Alright. So these are the basic things which our execution unit does. It also contains a branch unit for computing the branch condition. For example, you remember there are conditional branch instructions like BGT or BEQ, right. So those conditional branch instructions, they that computation is also done in the ALU only, because to check the condition you will be using compare instruction, and depending on the outcome of the compare instruction, BEQ or BGT will update the flags, appropriate flags, and that updation is also done at the ALU stage. So all these things is done in the execution stage. So it contains the branch unit for computing the branch condition. All right. So branch conditions like BEQ or BGT. It also contains the flag register, so which gets updated as per the status of outcome of the CMP instruction. So it contains the flag register, which is updated by CMP instruction. So we have already looked into this thing. So what we will do, we will now look into the hardware that actually helps us in getting these things done. All right. I hope this is clear. All right. Now we will look into the other two stages, basically memory access stage. So in the memory access stage, it's pretty simple in a sense, like it interfaces with the memory system and it executes the load store kind of instruction. So basically interfaces with the memory system. It interfaces with the memory system, and it executes the load store. Instructions. How about the register write phase? So, this writes to the register file, right. So, it writes to the register file in case of a so generally ALU, if ALU is updating a register, so that updation is done at this stage. If there is a call instruction, now remember, when there is a call instruction, you need to also update the return address. So in that case, the return address also gets updated in the register array in this phase. So the task which are done is writes to the register file, and in case of an call instruction, it writes to the array address. Basically return address register. Okay. In simple RISC, we said that this return address register is register number 15. Okay, if I remember correctly. Yeah. So what we have seen so far, we have seen that okay, we need to design this processor, we need to understand the design of a processor, and the thing we started with is that the processing has to be divided into multiple stages. The stages are instruction fetch, operand fetch, execute, memory access, and register write. In instruction fetch, we fetch an instruction from the instruction memory and then compute the address of the next instruction. In the OF, basically operand fetch stage, we decode the instruction. We also figure out which basically in the instruction different fields and what they are to identify different operands. So if the operands are in are registers, then we fetch the register operands from the register file. If they are immediate, then we basically convert those immediate values to 32-bit. If there is a branch instruction like unconditional branch or call return kind of instruction, then we need to compute the branch target using the offset value which is available in the instruction. And for doing all these things, we need to generate the control signals as well. In the execute stage, we perform all the ALU operations, arithmetic operations like add, subtract, multiplication, division, comparison, mod, etc., logical operations, etc. And it also contains a unit in the ALU which computes the branch condition. So basically it checks the flag status, and accordingly it gives an outcome whether the branch is taken or not taken. Basically branch if equal, branch greater than, all these conditions are checked here. It also updates the flag register depending on the status of the or depending on the outcome of the compare instruction. The other stage is basically memory access stage, which is solely responsible for load and store kind of instructions, and then there is register write stage where we update the register files either from the ALU outcome, or if there is a call instruction, then we know that we need to before we execute that routine we have to update the array register. So this at this stage also we will be using the RW stage. Okay, so this gives an overview of all the different stages of the processor. Now we will dive into little more deeper and understand each of these stages. So we will start. So what we are looking at now, detailed design of each stage, and so basically detailed design of each stage. So we will start with the instruction fetch stage. Instruction fetch stage is very simple. So I'll just project it here, so that we can save time in drawing. So this is what the instruction fetch stage looks like. So I'll just highlight. So this is your, this whole block is our instruction fetch stage. Now what it has? It is very simple. So it has this program counter. So this is a register, program counter register, and then there is so program counter, what it contains? It contains the 32-bit address where you can get the next instruction. And for our discussion, this is a, let's say, negative edge triggered program counter. So whenever the clock signal goes down, this negative edge arrives, the program counter. So whenever there is a single line and which has a stroke like this and a number written like this, that means this single line is representing 32 parallel lines. So this is a 32-bit address which we are passing from the PC. So PC is the register which contains this 32-bit address. We are passing it to the instruction memory. Now right now we don't have not discussed about memory, so we will treat it as a black box. So this is our instruction memory. We will come to it in our later part of the course. So depending on this address, I'll find out what I'll read some location and I'll get a 32-bit data or instruction. Basically 32-bit instruction I'll get, and that will be passed from this instruction memory as my instruction. So this is what I am trying to do in the instruction fetch stage. So I am reading, whenever the clock negative edge comes, I am reading the program counter, and the program counter is indicating a particular location in the instruction memory from where I am reading the 32-bit instruction. Alright. So that is the output, one of the output of my instruction fetch stage. Now I am not only doing that, I am also updating my PC so that whenever the next negative edge comes, I can do the same operation, because I have read this instruction which is indicated by this address. In the next clock cycle, I should read the next instruction. Now where this next instruction should come from? Now since our each of the instructions are 4 bytes, so if there is no branch instruction or there is no change in the sequence of instruction execution, then the next instruction will come from the current address plus 4, because our each of these instructions are 4 byte instructions. So that's why the next instruction will be located in a location which is plus 4. If I add 4 with this, then the next instruction location I will be able to get. So this is one option. So what I will do, I will add the current PC with 4, and that is one possible PC, next PC, okay, if there is no branch instruction. Now if there is a branch, then the address will be different. and that address will come from some other stage. So, we will not uh, uh, we will not talk about it at this point. In the decode in the next stage, basically this operand fetch stage, we will figure out, we will see that if there is an unconditional branch, then the new address will come from there, because there you will have a offset which you need to add with the PC, and that is how we will be getting the new branch. Or if even if there is a conditional branch which is evaluated in the execution stage, and you know that okay, the branch will be taken. So, basically there is a control signal which says that is branch taken. If the branch is taken, then you should take this new address as your update to update your PC, and if there is no, if the branch is not taken, then you will take this input as the new PC. So, just for completeness, I hope all of you understand what is a multiplexer. So, multiplexer is so in this case we need a 2 to 1 multiplexer. So, as you can see, this is a multiplexer. So, it has two inputs. Now, there is a select line. Depending on the select line status, for example, if the select line status is 0, then this input will be selected and it will come out as the output. If the select line input is 1, then this input will get selected and it will come at the output. Okay. Now, similarly, here we have this 2 to 1 multiplexer. It has a control signal which is basically looking for this condition, is branch taken. So, we have not discussed about control unit, but there is a control unit which is looking at everything, and it is enabling this signal whether the branch is taken or not taken. And if the branch is taken, then you take this new PC which is calculated differently, maybe from the offset, or maybe some instruction has already given. Basically, the offset value is given and it need to add it to the current PC to get the branch address or branch PC address, and you generate that, you pass it to the multiplexer. If the branch is not taken, then you go in the same sequence in which you were executing your program. So, basically you add 4 with this and you get the new PC address. All right. So, basically our instruction fetch unit is this simple. This is our instruction fetch unit. It has this PC, this extra mechanism. So, the next PC, what it will be is evaluated here depending on this control signal, is branch taken, and this input about new location from where the branch has to be or the PC has to be updated. So, what we do in this instruction fetch, we use PC to access the instruction memory to get the instruction. So, instruction fetch essentially gives us the instruction that need to be executed, and it also updates the PC. Now, how it updates it? Basically has a multiplexer, and the input to the multiplexer are either PC plus 4. So, this is nothing but PC plus 4 or a branch target, and depending on the outcome of this control signal, whether the branch is taken or not taken, you select appropriate output from this marks. All right. I hope this makes sense. Okay. Now, what are the possibilities of this is branch taken control signal? So, this control signal is branch taken is generated at the execution unit, because there may be some basically conditions you need to check to understand the output of the conditional branch situations. Some cases the instruction may not be a branch instruction. For example, if it is a non branch instruction, then this is branch taken will be always 0. You don't have to as soon as you can decode that, you can figure that out, that okay, since this is not a branch instruction, so each branch taken control signal does not make sense and it will be 0. There will be some unconditional branch like call, return, branch, etc., for which we know that the outcome of the branch, it is always taken. So, in those cases this is branch taken will be always high, so that you select the PC appropriately. Now, in case of branch if equal, there you need to look at basically the flags, and that is done at the execution unit. And if the branch is taken, if the flag is basically indicating that it is equal, then you will be taking branch. If the branch is not taken, then you will be basically initializing this value as 0. Similarly, branch if greater than is initialized like this. All right. So, I hope this makes sense. Now, there is a simple another concept which is worth discussing here, is called data path and control path. So, let me write it down, and it is very intuitive. So, data path and control path. So, a very loose analogy can be, let us say all the cars moving in the road are your data, all right. So, they are following the data path. Now, control is your traffic signals. So, the control of data is manipulated, or depending on the different control signals, you will allow some data to flow or to stop and so on. So, the data path consists of all elements in the processor that are dedicated for storing, retrieving, processing data, such as your register files, memory, ALU, etc. So, all these things come under data path, all right. And the control path is basically primarily contains the control unit, and whose sole responsibility is to generate the appropriate control signals. So, for example, here you see that the multiplexer needed a control signal. Now, all these things are part of your data path, your memory, your program counter, your all the other registers which are not there here, but everything else is your data path, but the control is done by this control signal, and that is coming from the control unit. So, that is your control path. Okay. So, it's not very difficult to appreciate that most of the things, like your, as I mentioned, like under data path, it contains all the elements in the processor that are dedicated for storing, retrieving, processing data. To give you some example, like register files, memory, ALU, all these things are part of your data path. Whereas in the control path, it primarily controls the control unit. So, it contains the control unit, and the interconnect switch passes those control unit to different appropriate locations, so that instructions etc. can be appropriately selected. So, movement of instruction, movement of data, those things are controlled by the control unit. All right. Okay. So, now just to quickly recap our all the instructions, because now if we move to the operand fetch, before that we need to understand what all were there in our what all instructions we were dealing with. So, this is just a recap we have already seen. So, there are 21 instructions. Now, there are these arithmetic instructions like add to mod, where basically you have a very similar pattern. All the instructions has a destination register, two sources. One is a source register, another can be a source register or an immediate value. You have this compare instruction where there is basically two sources you compare. So, one of the source can be an immediate value as well. Similarly, you have this arithmetic, basically this logical operations like and, or, not, etc., where it is pretty much similar to most of, basically and or are pretty much similar. So, you have a destination and two sources, and not has one source, one destination, one source basically, and then move also has one source. And then you have this load shift registers, shift instructions, and logical shift and arithmetic shifts, which also have the same format. No-op we will be looking at in more detail when we talk about pipeline, but yeah, we will look at them separately. Then there is this branch instruction. So, all the branch instructions which we have also highlighted earlier starts with 1. So, at the decoding stage it becomes very easy. So, if you see that the instruction, the most significant bit out of those 5 bits is 1, then you know that it is a branch instruction. So, you can very quickly decode it, alright. And then there are other instructions like load and store. You see that load and store also has some pattern, common pattern. So, you can detect this common pattern, and you know that okay, this is a memory, this is an instruction which deals with memory and so on. So, to classify all these instructions, we have seen this also earlier. We said that okay, the instructions broadly can be classified into this 3 broad categories. If the branch instruction, so in case of branch instruction you have opcode of 5 bits, and then there are 27 bits which are reserved for offset. So, basically it indicates like where you need to branch to. So, if you add this offset value, and this is again you have to remember that this is a word offset. So, that means this offset address indicate a 32 bit or basically point to a location, point to a data which is 32 bit. So, this is, that is why it is a word offset. So, we will have to shift or shift it by 2 bits to the left to get the complete 29 bit address. So, once we get the 29 bit address, then we convert it to a 32 bit offset value by basically extending the sign. So, that is how we will figure out the actual offset value which need to be added with the PC. So, we will see it in a bit. The format of instructions which deal with registers only. So, in that case you have again those 5 bits. So, these opcodes are fixed. So, 32 to 28, this block of bits are reserved for opcode. You have then this immediate bit. So, in case of register, this immediate bit will be 0, and then your destination register is stored, the address of the destination register is stored in this location 26 to 23. So, basically since we have 16 general purpose register, we need 4 bits to store the individual identity of individual registers. Similarly, you have your source 1 and source 2, which is stored in this location. So, 22 to 19 and 18 to 15. All right. So, this is your register instruction format. Now, the other instruction format which is also very important is the immediate. So, here we have similar 5 bits for opcode. This I will be 1 here in this case, because we have immediate value. Then the destination is a register which is having the same location where you can find the address. The source, and the one of the source is again a register. So, this is also fixed. Now, you have 18 bit immediate value, out of that 2 bit is your modifier, and the rest 16 bits are your actual immediate values. Now, each of these formats, when you are in the hardware, you are decoding the instruction or you are trying to fetch the operands. So, you have so remember where we are, we have already fetched the instruction, we have looked into the instruction fetch stage. Now, we are trying to look into the next stage where we are trying to fetch the operands, or also we are partially decoding the instruction. Now, in this stage the possibilities are these. So, I can have an instruction which has only 5 bit opcode followed by offset values. I can have an instruction which has the 5 bit opcode and then the 3 register addresses, or I can have a instruction where I have 5 bit opcode followed by 2 registers and then an immediate value. But in the hardware, I have just fetched the instruction, I only have this 32 bit, I have not done any other thing, I do not know what instruction it is. Now, one thing you can do is basically you can say that okay, I will try to first figure out by looking at or understanding what this opcode says, and accordingly I do some steps. Like if I know that it is a branch instruction, then I know that these are offset values, and then only I'll activate the unit which will calculate the PC plus offset. Similarly, you can say that okay, if I decode that it's not a branch instruction, then I'll not do this, or I'll not activate this. So, this can be done, but this also requires little more complications, and it involves more hardware, etc. So, we will see what will be the more reasonable approach for our simple RISC implementation. So, so what you can think of is that I have let us say 3 parallel units to deal with this kind of 3 different cases. In the opcode fetch stage, I will parallelly do these operations. So, I will assume that okay, this is a branch instruction, and accordingly I will try to figure out, I will find out the offset value and I will calculate PC plus offset. But it might be that it is not even a branch instruction. This 27 bits which I am considering as offset actually are some other values, maybe indicating some registers and some immediate and so on. But yeah, this is a trade off. So, you can say that I do not want to compromise on performance, and that is why I will parallelly employ 3 different modules to do these things without knowing whether the result will be useful or not. So, for example, if it is not a branch instruction, whatever I will be doing in this hardware is not useful. Similarly, whatever I will be doing in this this module If it is a branch instruction, then that will be not useful. But still, since I have already done it parallelly, so it saves lot of my time, and as soon as I figure out like which of these 3 modules are giving me the appropriate result, I can just pick that outcome, and ignore all the other things, or ignore all these other stages. So other stages, whatever it has done, it's basically garbage, it's of no use. But it basically saves my effort in and also improves performance. So let's now look at individually these 3 modules, and we start with the register module. So in this register file read module, so we know that from the instruction we will get the destination. So the destination is fixed. So the blocks of bits which denote your destination are fixed. So here you see that what we need to do. So let me go back. Okay. Yeah. So let's look at what are the instructions which deal with the register. So you see that all these arithmetic operations, so they have this destination register, they have this basically the 2 source registers. So we are not talking about immediate in this when we are discussing about register file read. And so in the 32-bit all right. So basically if we look at this, you see in case of register we have okay, opcode is fine. Now this is our source register from 26 to 23. The basically this is the destination register, this is the first source, and this is the second source, which we are getting from this part of the instruction. So 18 to 15 RS2, 22 to 19 RS1, and 26 to 23 our destination register. So these are the registers we need to read, because you remember that this stage we are trying to fetch our opcodes. So we are looking at the instructions which are dealing with only registers. So we need to fetch this destination. Basically we need to fetch our source registers. Destination is not the concern right now, but destination will come in picture because of one instruction. We will talk about it. Some of you might already remember. So now see, this is yeah. So this is our instruction. So after we get the instruction, we know that we need to read 2 sources. Now those 2 sources are this one, basically this one. So this is our RS2 and this is our RS1. So in a very simple scenario, we would have just basically passed these 2 registers, source registers. So what are these? These are the 2 addresses of the RS1 and RS2. These are 4-bit addresses, right? And this I give to the register file, and the content of these 2 source registers I get as output as my operand 1 and operand 2, because this is a operand fetch stage. So these are the 32-bit operands which I get, the data I get, right? This was the, if there was no so if all my instructions were only dealing with let us say source registers only, but there are certain anomalies. For example, I do have an instruction like let us say call instruction. Let me just so in case of a call instruction or a in case of a call instruction, there is an implicit. So what do we do while we have a call instruction? So of course we update our basically new PC with the appropriate location, but also we need to store the return address. Return address need to be stored in our array register, which is register number 15. It's a general it's a special purpose register. So in these cases we need to update this register. So in those case basically if there is a situation where we want to basically let us say we are returning from a call, and so let us say in this case return instruction. So if the instruction is returned, then we need to read the return address. So where I will read this return address? So that also has to be done in this opcode read instruction itself. So basically opcode operand fetch stage itself. So what I am trying to say, let me just rephrase. So let us say I have this instruction return. So I have this I have decoded this instruction. Now I have to figure out now I am in the operand fetch stage. So in the operand fetch stage, I know that in return has to return to the address which is stored in the return address register. So I have to read the return address register. So that will be my basically output of my operand fetch stage. So to address that, I will not only simply have RS1 and RS2 as my two possible inputs coming in this stage to the register file. I might also have a situation where RA15 will come here, and I have to read the content of the return address, and accordingly that content I have to give out as the output of this stage. So if the instruction is returned, so again the control signal will see if the instruction which currently we are currently is in the opcode fetch stage, if it is a return instruction, then we have to select this input, which is by default the address of RA15, and I will read this RA15, and that outcome will come as OP1 if this is a return address, if this is a return instruction. All right. Similarly, you remember that we did something with the store instruction. What was the store instruction? Store, we know that we need to store the value of this register to a particular memory location. The memory location is denoted by a offset and a base register, which is basically stored in, let us say, RS1, but the value which need to be stored, that is stored in our RD register. So we did not want to make things complicated, and we said that okay, we will make things simpler, and though this is in store instruction, there is no destination, right? There is no destination register. We are storing the value in a memory location. So the destination is a memory location here. But because the way the store instruction is, for example, if you remember, I will just give a simple store instruction. Let us say we have a store the content of R1 into this location, all right. Now, this is the formatting of the store instruction is such that this will be stored in our RD location. In the 32-bit instruction, the location which is reserved for RD, that will be used for storing this location of R1, but this is not the destination. Basically, this is from where we need to get the data which will be stored in this location. So, this register value will be stored in our RS1. So, this will come as the outcome of basically OP1, and this store basically this destination register, this will come from here, and just for the store instruction. So, here I have a control signal which says that is this instruction a store instruction. If so, then you take this input and read the content, and basically the data should be coming out as OP2, all right. So, to accommodate this store instruction, we need this mux. Similarly, to accommodate the return instruction, we need this mux, because depending on like for if this is a store instruction, then the RD needs to be read, which for any other instruction we do not have to do, and if it is a return address, then we have to basically read the return address, and that is why you have to read the RA15. So, hope this makes sense, all right. So, this is what you do in the register file read stage. So, just to recap what we have talked about. So, the register file has two read ports. So, these are the two read ports, read port 1 and read port 2, and so this is basically your you can think of your two inputs, the first input and second input, and you get these two outputs, basically the two operands, values of the two operands. Now, this first OP1 is basically a branch target address or return address in case of the instruction is a return instruction, RET instruction, all right. So, if this is not a return address, then this OP1 will be your source 1. Now, the OP2 again can have two possibility. If it is not a store address, then it is your source 2, then that is fine. And if it is a store instruction, then basically the output, the value of OP2 need to be stored. This is the value which need to be stored in case this is a store instruction. I hope this makes sense. Okay. Now, if we look at the other part, the immediate and branch unit. So, basically we said that the opcode fetch or basically operand fetch has this register part, and then it also needs to deal with immediate and branch kind of instructions. So, in this case basically it is the instruction you get, and parallelly, as I said, like irrespective of whether it is a branch instruction or not, you will do this work parallelly. So, what you will do, you will assume that the basically apart from the 5 bits which are denoting the opcode, the rest of the 27 bits are denoting offset, which you can use for calculating the branch address. So, you shift those 27 bits by 2 bits to the left, and then extend the rest of the 3 bits to get your 32 bit offset. You add it with your PC to get the branch target, in case this is this address you need to calculate. The other thing you do parallelly is basically you assume that this is an immediate instruction. So, the bits from 1 to 18 which denote the immediate bits, you take them and then use those immediate bits for calculating the basically looking at the offset, looking at the modifier, you calculate the 32 bit immediate value which you need to deal with. So, basically this thing is done parallelly. Now, you might as you can understand that there many a times you will be doing unnecessary branch target calculation or immediate evaluation, but as we have discussed, it is important to get things done well in advance, so that when you need them you do not have to wait for them. So, yeah. So, basically yeah, so these two things are also parallelly done. So, if we look at the operand fetch unit in totality, so this will look something like this. All right. So, you see that you have this part where you are trying to calculate the branch target, the immediate values, and this part which you are trying to deal with the register operands, and you are giving output as your operand 1 and operand 2 depending on what kind of instructions you have. So, you get this PC and instruction from the fetch unit. This is what your operand fetch unit is dealing with. Of course, there is a control unit which we have not talked about. Control unit basically selects for example, all these control lines which are dotted, for example, whether it is a return value, whether it is a store instruction, which of these things need to be selected, etc. So, these are done by the control unit, which we will talk about in a bit. So, in the to the control unit, the inputs are basically the opcode, the immediate bit, and basically opcode is nothing but instruction from instruction which are in the instruction 32 to 27, these 5 bits, and the immediate bits. So, these 6 bits are input to the control unit, and depending on those 6 bits all the control signals are generated, and these outcomes are then fed to the execute unit. So, okay, we will resume our discussion from here in our subsequent discussions.